Extreme Further.
Here I have a galvanometer, and what this is a very sensitive ammeter. And then if I just connect, I have a wire connected to one terminal and another wire connected to the other terminal. So we have a closed loop here, and it goes through the galvanometer. And watch what happens if I take a horseshoe magnet, like that, and pass it through the loop. So pass that through the loop, and I think you could see the needle is moving a little bit. So what would happen if I doubled it up? So we can see the needle's moving. That tells us that there is charge moving. So yeah, it looks like it's moving a little more by looping it around twice, like that. And then you could imagine we could extend this to, here I have many turns of wire. And if I take my horseshoe magnet and, oh, look at that. Pins the meter, right? And it looks like, does the speed affect it? If I go quickly, it does that. And if I move slowly, looks like it doesn't move as much. And direction matters. And if I stop moving, we don't get a current. This is how electricity is generated, right? This is called magnetic induction, right? And the way you generate electricity is you have a changing magnetic field going through a coil or a loop of wire. It's called magnetic flux, the field that goes through the wire. And you can see that we can generate electricity. All right, let's talk about magnetic induction. This is the creation of a voltage, or also called an EMF, in some sort of coil or something like that, due to a changing magnetic field. And before we talk about induction, we got to talk about something called magnetic flux. So let's imagine we had a magnetic field. Now keep in mind, this field exists in 3 dimensions, even though I have to represent it in 2-dimensional space. So it's out in 3-dimensional space. It's out here too. It's called a magnetic field, or the B field. This is also called the magnetic flux density. And it's you can just think of it as the magnetic field, and we've drawn the magnetic field lines. Magnetic flux is how much of the field goes through some sort of opening. Usually from a practical standpoint, we're looking at a coil, and the flux is how much of the field goes through the coil, right? So if I were to try and draw this in 3 dimensions, and I had some sort of loop of wire like this, right? That has some field going through it. So this has some magnetic flux. The amount of field that goes through the loop is called the magnetic flux. And this loop has some flux through it. And if I drew this loop has more flux going through it, right? Because it's a bigger loop. It's in the same uniform field, but it's a bigger loop, so more flux can go through it. So for a given field, you could increase the flux through a loop by making the loop bigger or having a bigger loop. But there's something else you could do too. let's let me extend this a little further, like that. And let's take a look at this loop here. I could take this loop here and turn it a little bit. You know, let's say that's the same loop. Hopefully I drew it about the same size. Okay, it's the same loop in the same field, but it's been reoriented now. Now there's less flux through it, right? The amount of field that is going through this is less than this one, because this is at right angles, this is at an angle like this, and you could imagine, right? So I got like this. If I want to maximize my flux, I'm going to want it like this. If I turn it like this, it's less. And in fact, if I go sideways like that, no flux is going through the coil. Okay? So that's magnetic flux. It's the amount of magnetic field that's going through some sort of opening. We could change it by changing the size of the opening or reorienting the opening, or we could change the field, right? For this one, if we cut the field in half, right? If we, for this particular, let's not worry about this one right now. So for this particular loop, if we made the field smaller, right? We have less field now. There's less flux going through it, right? So we could change the flux by changing the size of the loop, by changing the orientation of the loop, or by changing how much field you have. What's the amount of magnetic field? So you can think of the magnetic flux as how many lines of flux, how many lines of these magnetic field lines are going through an opening. That is called magnetic flux, right? And this B field, which is a vector field, is called the magnetic flux density, right? So this tells you how much flux there is in a given area, and then if you give me the area and the orientation, I can figure out how much flux is going through a loop. Now it turns out that if you change the flux that goes through a loop of wire, a potential difference will be set up in the loop so that if it's a closed loop and current can flow, that the loop is going to set up a current to create a magnetic field to prevent the change in flux. You can think of it as, nature doesn't like things or stuff like that, but nature doesn't like a changing magnetic field, and it's going to do whatever it can to stop the magnetic field from changing. It's kind of like magnetic field inertia, right? Nature doesn't like a changing magnetic field, so it is going to set up a potential difference that could possibly set up a current that would cause prevent the change in the magnetic field. So let's take a look at how this works. You can imagine we have a bar magnet like this, and this is the north side and this is the south side, and it's got magnetic field coming out of here, and it goes like that and loops around, something like that. Okay, I'm not going to do a great job on my drawing. But anyways, it goes like that. That's what it looks like outside. And then, of course, it forms closed loops inside. And there'd be more lines, but I'm not going to draw more. And then if we have a loop of wire like here, so here the loop is going behind the field, and now it's going in front of the field. So basically we got this. Here's our magnet, and here is our coil. And this thing is dropping down, right? Let's give it a velocity downward. So it's moving downward, right? All right. So it's going downward like that. So we're going to talk about something called Lenz's law. And that says that this loop, because there's a changing flux through this loop because this thing's moving, the magnetic field is getting larger as this falls towards it. It's going to set up an EMF, a voltage EMF stands for electromotive force, and we can just think of that as a voltage though. So it sets up a voltage, and because it's a closed loop, that voltage is going to create a current to try and create its own magnetic field to stop the changing magnetic field. All right? So there's a downward magnetic field and it's increasing. Now, it wants to stop that increase. So what's it going to do? It's going to try and create an upward magnetic field to counteract the increasing downward magnetic field. So how's it going to do that? It's going to do that, and we can figure out the right-hand rule. It's going to set up a current because it wants a field this way. I'm going to use my thumb like that. So I want a field upward. So I'm going to wrap my fingers like that, use the right-hand rule in a coil, and it is going to set up a current like this, going around the loop like that, to prevent that changing magnetic field, and it's going to create its own field. So this is going to go like that. So this is going to create a B field this way, attempting to prevent that increasing downward field. It's going to create an upward field to stop the increasing magnetic field. That is Lenz's law. It will set up current like that, and this is how we generate electricity. We change a magnetic field through a loop of wire that creates a voltage, and then if there's a closed loop, there will be a current. It will create a current. All the electricity that you experience is caused by this. Okay, this is called magnetic induction. And Lenz's law is how we determine what is the direction of the current. Okay, so let's try another one. Let's take our bar magnet again. It's let's say it's falling or going down. It's got a downward velocity. That way is north. That way is south. And we have our we have a loop of wire here. Like that. All right. This is the front of the wire. And this is the back of the wire. Right? It's hard to draw this because we're in 3 dimensions. But there you go. So we got like that. This lower portion is the front, and that's the back. All right. So that is falling down. Like that. The field from this is going through. This has some flux due to here. It's close enough that there's some flux. Why don't you see if you can figure out what's the direction of current through this coil due to the changing flux. Why don't you give that a try right now? Draw it, figure it out using Lenz's law. Figure out the direction of the magnetic field that's through here. Think about how is that magnetic field changing? And what is this going to do to prevent that change, the changing magnetic field? All right, give that a try.
Pause the video now.
All right, I'm going to draw the B field due to this in pink again. So we had something like this. I'm not going to draw looping around. We just need to know that we got a field coming out of the north end. And I'm not going to draw looping around just for simplicity's sake. And then the south has a field like this. Right? It has a field like that. You know, we're looping around and stuff like that. I'm not going to draw the loops because we got enough to deal with here. But this field, as it falls away, we got a downward field. Is it getting bigger or smaller? Right? As it gets farther away, is that field getting bigger or smaller? The flux that's going through there, bigger or smaller? Right? It's getting smaller. Right? This is getting farther away. So the field's getting smaller. Doesn't like that it's getting smaller. It has a field going through here and it's getting less. It's going to do whatever it can to prevent that field from getting smaller. So what's it going to do? I'm going to use blue for the field caused by the current here. So it wants to create its own field like this. It doesn't like that the field is getting smaller. So it's going to create a field to prevent it from getting smaller. So its own field in the same direction as the existing field, right? It doesn't like a changing field. It's going to try and stop that change, right? So it's going to go like that. And so how do I figure that out? I have to use the right-hand rule. I got a coil like this, and I want a field that's going down like that. So it's going to, the current is going to wrap around like that. I'm going to use that right-hand rule. And so this is going to have a current like this. The current goes like this in the wire, right? Current's like that, going around like that, right? Boom. Right, that's the induced current due to this changing magnetic field. Let's try another one. I did this in that Zoom class the other day. Let's say we had a wire that's bent like this. And this is a bird's eye view. All right, so let's say we had a wire that's bent like that, has no insulation on it. And then on top of this wire, we laid another wire without insulation. So we have a closed loop here. This wire is free to move on here. And let's say this wire is in a uniform magnetic field that is into the page. So we have a field that's into the page, a magnetic field that's into the page, right? Boom, something like that. All right. And this wire is moving down with a velocity like that. What is going to be the direction of the current? That's induced in here. Now this could be done one of two ways. We could use Lenz's law to figure that out. Why don't we do that first, and then we will use stuff we've learned before. There's another way to do it by using ideas that we learned before, where we have moving charges in a magnetic field. But let's use Lenz's law here. We have the field isn't changing, but this wire is changing. So the flux that is going through this opening is getting smaller, right? So why don't you take a moment to see if you can figure out what is the direction of the current in this loop of wire. Is it like this, or is it like this? Due to the changing flux as this gets smaller. Now, the flux in this case, again, is changing because the opening is getting smaller. That's the only reason the flux is changing. So why don't you take a moment to do that, see how you do.
Pause the video now.
All right, so here we go. All right, so we got a magnetic field this way, right, into the board. And the flux is getting smaller. So we got a field this way, and we got flux this way. The flux is decreasing. It doesn't like that the flux is decreasing. So what's it going to do? It wants to create its own magnetic field to stop the decreasing flux. So I'm going to use green, right? So the flux is this way, and we're getting less of it. So it doesn't like we're getting less. So it wants to create its own flux. It's going to go like that, right? Increase the flux by doing that. That's the flux that's going to be increased by current in the wire. How do I set up a magnetic field into the board? Well, that's in the board. My thumb is in the direction of the magnetic field. My fingers wrap in the direction of the current. So there's going to be a current this way. It's going to go around this way, right? All right. Now, let's take a look at this another way. Let's not use Lenz's law. Let's use ideas that we've already worked with. And in this case, we could solve that way. Because if this thing's got a velocity this way, there are charges in this wire, right? There are charges in this wire, and they have a velocity. They have a velocity downward like that, right? And we know that there's going to be a force on those charges because we know that there's a force on charged particles, or on charges that travel through a magnetic field. F equals QV cross B. We have a V and we have a B, and in here there are charges that can move. Now the charges that can move are electrons, okay? But current is defined as the direction a positive charge would move. So we're going to imagine moving positive charges. That's going to make our life easier, right? So why don't you take a moment and use this to figure out what would be the direction in the wire.
Pause the video now.
All right. Of course, the answer's not important. We already figured out the answer. So let's make sure it's the same, though, right? So what do we got? We got QV cross B. Well, Q is positive because we're looking at the positive charges. V cross B. I got V. V's down. Crossed with B. Well, I can't. I got to bend it into the board. So I have to go V cross B. V's down and B's into the board. That means in this wire that's going down like that, there's going to be a current this way, right? And that's exactly what we found out before, right? The current goes around that way, right? So we got the same answer using Lenz's law and this idea that the force on a charged particle is QV cross B when it's in a magnetic field, right? So that is magnetic induction, right? And it's very powerful. It's how we generate electricity. If we didn't understand this, we wouldn't have the modern world we live in today, right? All electricity is generated this way. Generally, what they do in electrical motors is what they have is, or electrical generators. What they do is they have some sort of magnetic field like that, and they take a loop of wire like this, and the way they change the flux through the wire is by rotating the loop. And so you got to turn something. So like if you went to Niagara Falls and they got those turbines turning, what the turbines are doing is turning coils through magnetic fields, right? So right now, there's no flux going through the coil. So now the flux is increasing. Because the flux is increasing, it's going to induce a voltage in the wires, and there will be current flowing, and the flux is going to be maximized here. And now it's getting smaller, and 0, and then bigger. And this actually, the direction of the current will keep changing. This is how we create what we call our alternating current, or our AC voltage in our power lines. And they do it by turning, like this is how an electrical generator works. All right? So that is magnetic induction. Right? All right. It gives us our wonderful modern world. Anytime you have a changing magnetic field through a coil, you can generate electricity. So I did that in this case by taking a permanent magnet and moving it through the coil. And we got current going. But what I could also do is take another coil. Got another coil like that. And I could put it on top of this coil. So they're not electrically connected. Right? This it doesn't look like it, but this has insulation on it. This reddish material is insulation. I don't know if you can see. I've scraped the insulation off here, and it's more of a copper colored. It's a similar color, but not the same. You can see here that I've scraped off the insulation at the end here, and it's more of a brownish color. And this part's insulated. So these are insulated from each other. And if I just take a battery, I'm going to take a battery and put a voltage across this one, and that's going to cause current, and that's going to mean that there's a magnetic field here. This is going to act like a bar magnet, and that magnetic field is going to that flux, the magnetic field coming through here is going to go through here, and it's going to be changing because it goes from 0 to a non-zero value. And you'll see every time I tap it, boom, you can see we get current. So what I'm going to do here is I'm going to, okay, so I have the current going, it's going. I'm not inducing any voltage until I stop the current. Then I have a changing magnetic field, and then you saw. So again, start the current. Oop. Why am I not getting anything? All right, so, all right, current going, stop the current, And because stopping it changed the magnetic field, that induced a voltage in this coil, or it induced a voltage in this coil, and there was current flowing due to that voltage. All right, so that is magnetic induction, and this is how electricity is generated, by changing a magnetic field through a coil. You get current that can flow. You get a potential difference. All right, let's take a look at another type of generator, and that is the electric guitar. I actually built this electric guitar. A lot of people are surprised. I don't know why. They think I'm just some sort of talentless teacher who's incapable of doing anything other than teaching physics. But no, I'm a bit of a craftsman, and I built this myself. It's only a one stringer, but it is indeed an electric guitar, and it plays just fine. And one misconception that some people may have about electric guitars is that you plug them in and it's getting power from the wall that somehow gives you the sound. But that's not true at all. Electric guitar is a generator, right? It's an electrical generator. So here I have my guitar. It's a single string, and if I turn that on, you can actually hear it, and I can play a little slide. So what's happening here? We have, let me turn that off. Now, this is actually a generator. What we have here is, if you take a look in the middle, we have a magnet, right? You have a magnet right there, right in the middle, and you can see it's stuck to that. And wrapped around it is a coil. And the only purpose of the magnet is, if we take a look at the side here, it's to put this ferromagnetic string in a magnetic field. So we have a magnetic field coming out, and that causes this string, which has iron in it, to act like a magnet. It is a magnet at this point because it's in a magnetic field. So now I have a magnet that is oscillating over a coil. So now we have a changing magnetic field through the coil. That induces a voltage in the coil, and so we get a potential difference here. So then I send these wires into my amplifier, right? Okay, this isn't sending this. Your amplifier doesn't send electricity into here. Electricity gets sent into the amplifier. It amplifies it, and there's a speaker in here, and then I can play. I can rock out, right? Uh-oh. I don't have any sound. Ooh, had a bad connection. Oh, I see. I was shorting it out right there. There we go. See if I can get a little distortion. I don't know. Not really. Uh-oh. Anyway, there's my electric guitar. And now I'm not getting any sound out of it. There we go. I got some noise in my potentiometers. Boy, I think I have a career in music, I think. All right. electric guitar is a generator. Here's another electric guitar. This one I didn't build. And if you take a look at these, these are little magnets right here. It's exactly the same thing. What they've done with these plastic things, they covered up the coils. This is called a pickup, and this one has a pickup for every string, and then there's actually 3 of them here. So this string actually has 3 different pickups to give you different sounds. This is a little more sophisticated, but sometimes I think simpler is better, right? So anyway, there's my electric guitar. It is an electric generator. All right. You'll see sometimes, I've seen guitarists, you can actually scream into the strings and it will vibrate and it acts like a microphone. But anyway. All right. There you go. In today's physics challenge, I have an aluminum ring on a string, and it's swinging back and forth, and look at how fast it stops. That pendulum should be going a lot longer than that. But when I have that horseshoe magnet there, it stops pretty darn quickly. So why is that? Look at that. I mean, you know, the pendulum should be going for a long time. There's not much slowing it down. It's got mostly just mechanical energy, as we've learned, and it just swings for a really long time if left by itself. But when we put the horseshoe magnet there, it doesn't swing very long at all. So why is that? Figure out the physics. Why is that happening? This isn't a 2-word answer or anything like this. This is going to require analysis. Keep in mind that is an aluminum ring, and aluminum is not magnetic. Aluminum is not attracted to a magnet or repelled. It's not a magnetic material. Whoa, what's happening there? Look at that. Right? Not even touching it and causing it to swing without touching it. Well, it touched it there. And now it's stopping. All right, see if you can figure out what's going on there. All right, next we have another ring on a similar string, and note that when I get this swinging, it doesn't stop. It just keeps swinging. Right? This is behaving differently than the other ring. See if you can figure out why. What's going on here? Why is this one not stopping and the other one did? And they're both swinging through that same horseshoe magnet. That's baffling. This is a heck of a challenge. All right, good luck figuring out what is going on there.
It's true.